Verifying trig identities, example C. So let's take a look and see what we want to do here. I don't know if there's any obvious algebra to be done, so I think I will switch to sines and cosines here on the left side. Cosecant will become 1 over sine. Cotangent will become cosine over sine. And then those two fractions on the bottom can easily be subtracted. There's already a common denominator there. I'll end up with 1 minus cosine theta over sine theta. This is one of those complex fractions, so I should simplify it next. The only little denominator is the sine theta, so I'll take that and I'll multiply top and bottom here by that sine theta. That gives me sine theta on top, and then on the bottom those sine thetas cancel, so I have 1 minus cosine theta here. So I look to the other side, I still am not matching. There's not really any other obvious algebra step to be done. And so in these cases, a trick that we can use is called multiplying by the conjugate. If I'm not sure what else to do, but I see a fraction with a denominator consisting of two terms, I can try this multiply by the conjugate. The conjugate just means the same expression that you have down here, but with a different sign, S-I-G-N, in the middle. So this one says 1 minus cosine theta. The conjugate would just be 1 plus cosine theta. Now I can multiply that on the bottom as long as I also multiply that on the top. And it might not be readily apparent to you why I would want to do something like that, but take a look at what happens. On the top, I think I'm going to wait for a second on multiplying that out. I can always do that later if I so desire. It's the bottom I'm really interested in though, because do you see I have one of those a plus b, a minus b situations? Well, when you have a FOIL problem that's in that pattern, the middle terms always cancel out. You're going to get the 1 times 1, but the outer will be plus cosine theta, the inner will be minus cosine theta, so those go away, and then the last will just be cosine squared theta. With trig functions, this can be so helpful because, of course, I've created here a situation with a cosine squared and a 1, and that immediately makes me think of the Pythagorean identity. It's just the main Pythagorean identity, right? Sine squared theta plus cosine squared theta equals 1. If I move that cosine squared theta to the other side, this will say sine squared theta equals 1 minus cosine squared theta. Well, that's exactly what I have here. So in my next step, which I'll continue over here, the numerator doesn't change, but 1 minus cosine squared theta is sine squared theta. Well, do you see why it was a good idea that we didn't multiply out the top? The top is in a factored format. So is the bottom. Sine squared theta means sine theta times itself. Well, I have a common factor there I can divide out. This sine theta divides out one of the sine thetas down there, meaning I now have 1 plus cosine theta on the top and just a single sine theta on the bottom, and that's exactly what we were trying to match. And so we have verified this identity. Thanks for watching.